Hello everyone, and thanks for watching Edupedia World Videos. Now we'll begin a new unit called Gravitation, and in this video we'll study a concept called Gravitational Field. Newton was the first person who really quantified gravitation, and what he said was essentially a combination of three statements. He said that if you have two particles of masses m1 and m2, then m2 will attract m1 towards itself with a particular force which has a magnitude F and a direction towards m2. Similarly, by Newton's third law, m1 will have to attract m2 by a force of the same magnitude F but the opposite direction, that is towards m1. Newton said that this magnitude of the force is proportional to m1. He said that this magnitude is proportional to m2. Directly proportional, meaning if m1 doubles, the magnitude of force becomes double as well. And he also claimed that the force between them is inversely proportional to the square of the distance between the two. If this whole distance is r, then he said F is inversely proportional to r square. That is, if r doubles, F would become 1/4. If r would become 1/3 of its original value, F would become 9F. These three statements can be combined into a single statement. F is equal to G m1 m2 by r square. m1 is the mass of the first object, m2 is the mass of the second object, r is the distance between the two objects. Remember, we are talking about distance between the two objects because right now we're only talking about particles, right? We're not talking about extended bodies. G is the universal gravitational constant. It is a constant of proportionality. And its value is equal to 6.67 into 10 to the power minus 11 standard units. I'm not going to write the units right now because we've already seen that stuff before, right? It will be, if force is in kilogram meter per second square, you multiply it by meter square and you divide it by kilogram square, right? This is in standard international units. So this means that if we have two objects whose masses are 1 kilogram each and they are separated at a distance of 1 meters, then they will attract each other with a force of 6.67 into 10 to the power minus 11 newtons. Now that's a very small force, and that's why we realize we generally do not see gravitational forces when we are dealing with everyday objects because the gravitational constant is just too small. But when the mass keeps on increasing, that is, we deal with bigger and bigger objects such as the earth or the moon or the sun, then m1 m2 by r square becomes much more than g, and that is when the gravitational forces seem to have significance. So in our daily lives we only encounter gravitational forces when at least one of the two objects has an enormous mass, such as if the earth attracts an apple falling towards it. That is because the mass of the earth is very large, right? Now one thing to note here is Newton also said when it came to mechanics that F, the force experienced by an object, is proportional to the mass and F is proportional to the acceleration, and from that we deduce that F is equal to ma. But why didn't we write F is equal to gma, or taking another constant, kma? In other words, why didn't we take a constant of proportionality here, though we did take it here? The answer to that is, when we wrote this equation, which came before this equation, we had not yet defined a unit of force. So when we say force is proportional to the mass and force is proportional to the acceleration, and mass and acceleration are in kilograms and meters per second square, then we say F is equal to kma, which means that when the mass doubles, the force doubles. However, what unit do we want to define for force? So let's say I choose two separate units. In this case, I choose a unit called Newton. At this moment, the unit isn't defined yet. We've just given it a name, and we need to define it. So we define 1 Newton as 1 kilogram multiplied by 1 meter per second square. This is the definition of 1 Newton, and that is why we do not use any constant of proportionality, because we've chosen the constant of proportionality to be 1 because we are using this freedom in defining the unit. Now, I could similarly do the same thing in gravitation and I could say F is equal to actually m1 m2 by r squared, not gm1 m2 by r squared. But now I define this in a new unit. Let's call this Isaacs, in honor of Isaac Newton, who created this whole thing, right? So then we could say 1 Isaac equal to 1 kilogram multiplied by 1 kilogram divided by 1 meter whole square, right? So we have two separate units. One is in Newton and one is in Isaac. That is not really practical, because if we want to communicate freely among different people, we need to have a particular standard unit, and as it happens, that standard unit is taken to be Newton. So we can choose the constant of proportionality to be 1 in the first case when we are trying to define a unit. However, if we want to define other formulas such as this in terms of kilogram, meters and newtons, then we cannot say 1 Newton is equal to 1 kilogram multiplied by 1 kilogram by 1 meter whole square, because we've already defined a Newton to be this particular value, right? So if we want to use Newton anywhere else, we've already defined the Newton, and we have to use an experimental fact about the force between two objects of mass 1 kilogram each at a distance of 1 meter, and we find that that force is equal to 6.67 into 10 to the power minus 11 newtons. I could call it to be equal to 1 Isaac, and that would make gravitation easy, because this would be equal to 1. But every time I wanted to equate it with a mechanical force or an electromagnetic force, I would need to change Isaacs back into newtons, and it's not really practical, right? So the first time when we are defining a unit, we can define it to be any particular value, right? But once we've chosen the value of that unit, anytime else we use that, we do not have the freedom to choose the constant of proportionality equal to 0. Right. Let's look at a simple example of how these questions might work out. We have an object of mass 5 kgs and we have an object of mass 2 kgs, and let's say there are 7 meters apart, right? So they both will attract each other with the force of gravitation. Let's assume for now, unless I mention otherwise, let's assume that the floor is smooth. So there is no frictional force acting. On this 5 kg block, we'll have 50 Newton acting downwards due to the earth, and we'll have a normal force acting upwards, and they both will cancel each other because it's not moving in the vertical direction. The same goes for this object. Now F will be equal to, I'm just going to write it in terms of G because it becomes easier, G into 5 into 2 by 7 squared, right? That becomes 10G by 49, right? This is the force acting on each of them. What is the acceleration of the 5 kg block? It is the force divided by the mass, so that will be 2G by 49. And what is the acceleration of the 2 kg block? It will be 5G by 49. But they will be in opposite directions. The acceleration of the 5 kg block is towards the right, and acceleration of the 2 kg block is towards the left. Now what if I were to try to calculate M5, mass of the 5 kg object? It's 5 actually, so it's redundant. M5A5 plus M2A2. That gives me this multiplied by 5, 10G by 49 towards the right, plus 10G by 49 towards the left, which gives me 0. But this is equal to actually M5 plus M2 times the acceleration of the center of mass. This is the definition of the acceleration of the center of mass, right? M1A1 plus M2A2 by M1 plus M2. So which gives me the acceleration of the center of mass is 0. Right? Now this is a result which we've already seen before. If we, in this case, we took these two to be individual systems, but if we take this whole thing to be a combined system, in that case this F becomes an internal force. Internal forces cannot move the center of mass. Right, so this is the result we saw previously. What if in this question I was asked, where will both these objects meet? Right, so let's say after a few seconds, you could try to calculate it directly by using the acceleration and saying the total distance 7 meters, assuming they both start from rest. You could say 7 is equal to half into A5 into t square plus half into A2 into t square. Right, and that would give you t, and you could use t to calculate where they would meet. But an easier way would be, we know that the center of mass, which is somewhere here where this is 2 and this is 5, we know that the center of mass is going to stay at rest. And if these two objects are at the same place, the center of mass is going to be at that place as well. So we know that they are going to meet at the center of mass. That is, they will meet 2 meters away from the 5 kg object. Right? So this is an example in which I showed you how to calculate standard quantities in any simple gravitational problem. Let's move on to the main concept we'll study in this chapter, and that is gravitational field. Right? Now, gravitational field, first of all, we need to know why do we use this concept? Why does it make things easier? Right? So, let me just give you an example in which, let's say I have a two-dimensional plane and there's an object of mass 1 kg at the center. Right? So, in this case, this is my setup to a problem which I'm asking you. The problem is there's another object of mass 5 kg at a distance of 1 meters. What is the force acting on this object? Right? That is the problem. We can do it easily enough, and it will be g times 5 times 1 divided by 1 square, that is 5g in this direction. Right? And if we kept particles at other places, I'm sure we could find forces on those particles due to this 1 kg particle as well. Right? Now, if I wanted to find the force on this 5 kg object, I could give you the problem in another way. Right? And instead of saying that we have an object of mass 1 kg at the center, I could just say that wherever you put an object, you could put an object here or here or here or here or here. Wherever you put an object, that object will experience a force. The mass of the object could be changing, let's call it m, will experience a force of m times something. Right? This something is called the electric field. Let's use vectors for now. I'll get to the vector form of the previous equation in a minute. Right? So this whole thing is E. In this case, what would this E be? If this 5 kg we take it to be m kg for a second, the force will be m into 1 by 1 square towards this direction. If we even generalize this and take it to be r meters, then it becomes m into 1 into, sorry, this shouldn't be there, this should be g, m into 1 into g by r square. Right? So E comes out to be 1 into g by r square radially inwards. Right? Now this E, the gravitational field, essentially it is nothing but the gravitational force per unit mass. So either I could have said we have a 1 kg object placed at the origin, or I could have just said we have a particular configuration of charges such that an object placed anywhere at a distance r away from the origin will experience a force per unit mass of 1 into g by r square towards the center. These two statements are equivalent. I'll repeat them again. The first statement saying we have an object of mass 1 kilogram at the origin. The second statement saying we have a particular configuration of these charges. You don't need to know what the configuration is, but that configuration of charges results in a force on any object of mass m, results in the force per unit mass of any object rather, to be equal to 1 into g by r square towards the origin. These two statements are equivalent, but in this case you might wonder why we need the second one at all, because the first one is somewhat easier. Well, the answer is, a lot of times we are given the electric field, that is, we are given the force per unit mass any charge would experience, but the charges required to create this field might be complicated. And when we deal with electric field, we do not need to worry about what charges created this. Right? So, as another example, let's say we have a two-dimensional plane and we have an electric field equal to 5 I cap. That is an electric field equal to 5 units towards the right everywhere. Right? That means if I keep an object of mass 10 kg, it will experience a force towards the right of 50 Newton. Because an electric field, one thing I'm really sorry about, I might be saying electric field instead of gravitational field. That is because electricity and magnetism and gravitation are pretty much similar. In gravitational concepts, you have gravitational forces, gravitational fields, gravitational potential energy. Similarly, in electricity and magnetism, you have electromagnetic fields, electromagnetic forces, electromagnetic potentials, energies. Not only is that a similarity, you have the 1 by r square dependence in each of them, right? Electric force is k q1 q2 by r square, gravitational is gm1 m2 by r square. So the mathematics of them is pretty similar, and a couple of times you might see me mentioning electric field, and I apologize for that. What I mean is the gravitational field. Right now we are only talking about gravitational fields. Right. So we could say that there is a gravitational field of 5 I cap everywhere in space. And that simply means an object of mass 10 kg experiences a force of 15 Newton towards the right. An object of mass 0.2 kilograms experiences a force of 1 Newton towards the right. Now you can see why this concept becomes easier, because it's easier to say the electric field everywhere is 5 I cap than to actually give a configuration of charges which would create such a force. Then to actually create a configuration of charges which would guarantee an object of mass 1 kg always experiences a force of 5 Newton towards the right. Okay, and a lot of times we are interested in a particular particle or its trajectory. Now, what the configuration of charges is which applies a particular force on a particle is irrelevant if we are just talking about the particle, right? If I say to you that we have a two-dimensional plane with a particular electric field everywhere, right? Electric field is a vector which has a position, which has a magnitude and direction at every point in space. Let's assume this is the electric field, right? And I've given you at every point what the electric field is, magnitude and direction. So to calculate how much time it will take from an object of mass m to go from this point to this point, I just need to know the forces acting on the particle. Right. Now these forces or this electric field could have been set up by 5 different particles in a particular place here, or they could be set up by 3 particles here. It doesn't matter if all we need to do is calculate the motion of this object. Right. So the electric field helps us to forget about what configuration of charges actually cause this particular scenario. We only have to focus on the particular scenario. Right. So this often makes things quite easier. Right. Now we'll take some particular standard shapes and try to calculate the electric field and the gravitational field and the gravitational force due to them. The first case is the standard point mass. We have a point mass that is a particle, and you want to find the gravitational force and the gravitational field due to this particle. Let's say this is the particle which has a mass m, right? Then any other particle of mass small m will experience a force of, the direction is clear right now, it will be in this direction, right? So it will experience a force of gmm by r square. This is the force, but this force is equal to m times something. Remember, the force experienced by a particle of mass m is equal to the mass multiplied by a constant. That is what Newton's gravitational law implies, right? The first statement I wrote was F was proportional to m. That means F was something multiplied by m. What is multiplied by m in this case? It is G capital M by r square, right? So this is the electric field. So the electric field is G capital M by r square. Notice that if you are talking about this point mass, to calculate the force exerted by this point mass, I need to know the mass of the particle on which the force is being exerted. But to calculate the gravitational field due to this mass, I do not need to know the other masses. The gravitational field is simply the force which 1 kg object would experience. If you want the force of a 10 kg object, you just multiply it by 10. Right. So for a point mass, F is gmm by r square and electric field is gm by r square. By the way, let's talk about vectors for a second. When we say F is equal to gmm by r square, that could also be written as F is equal to this times minus r hat. And that is assuming that the first particle is kept at the origin and the second particle is somewhere else, right? So magnitude is F gmm by r square. This is the direction r hat, right? The unit vector in the direction of the position vector. This is the position vector. The direction of the force is in this direction, that is minus r hat. right? So this is the vectorial form. After point mass, let's look at a slightly more complicated case. Let's look at a ring. This is a circular ring which we are looking at in the plane of it. That is, the plane of the ring is perpendicular to the plane of the monitor, right? If to make it a little bit clearer, I could probably draw arrows like this, right? On the top, it is going inside the monitor away from you, and at the bottom it is coming towards you, right? It's difficult to draw it, especially with a tablet on a monitor, but I hope you understand it. This is going away, the topmost point, and this is coming towards us. It actually doesn't matter what is going and coming, that's just arbitrary, but the sense of this ring should be clear to you. This is not an oval which is in this two-dimensional plane of the monitor. This is a circular ring which is perpendicular to the plane of the monitor, right? Let's say this ring has a radius r, and we want to find the gravitational force and the gravitational field due to this ring at a point A away from it, right? And let's say the mass of the ring is capital M, right? So if we want to find the force on a particle of mass small m, we'll do the easier thing. We'll first find the gravitational field at this point due to the ring, then the force will just be the field multiplied by the mass of this point, right? So in this case, we'll have to take the gravitational field due to individual elements and add them up, right? So let's take a random element. Let's take the element at the top first, right? So there's a small element. Let's take its mass to be dm for now. The total mass is m. Let's take a small element of mass dm at the top, right? The gravitation, now this can be thought of as a point particle. So the gravitational field due to this will be g into dm by r square. But r will be now this distance, right? If this is r, this is a, this distance is root of r square plus a square. So this will be by r square plus a square. This is the electric field, the gravitational field due to this mass. The direction is this, right? Now if we take this angle to be theta, this particular force has two components, one in this direction and one perpendicular to this direction, right? Similarly, if we look at this particular point, if we take it to be a mass dm, it will exert a gravitational force, a gravitational field in this direction. Again, it will have two components, one in this direction, the other in this direction. By symmetry, the force magnitude will be equal. It will be g dm by root of r square plus a square, and the angle is equal because the radius is the same on both the sides, right? So we see that the magnitude of the force will be equal, and their horizontal components will add up, but their vertical components will cancel. Similarly, if we take any two diametrically opposite points, if we take this point, right, it will have an electric field in this direction. Now this angle is not smaller, it's like a cone. And if we take the opposite point here, it will have a gravitational field in this direction. They both will have components in this direction which will add up, and they both will have components in the vertical direction which will be the opposite of each other, right? They might not necessarily be in the vertical direction, but they'll be in the plane of this ring. So again, we see by symmetry as well that if every point attracts this point with a gravitational field in such a manner, then all these points will add up and give me a net gravitational field in this direction, because the perpendicular components will all cancel. So why don't we write the component in this direction and add them up? That will simply be this force multiplied by cos theta, right? Cos theta will be a by root of a square plus r square. So this is the component of the gravitational field due to a small mass dm towards the ring. Now we can integrate it all, but all of these quantities are a constant, so dm becomes m, the total mass, right? So we found out the relation that the gravitational field due to a ring is given by gma by a square plus r square to the power 3 by 2. We see that it's 0 if a is 0. That is, if we keep an object at the center, the gravitational force will be 0 because it will be symmetrically attracted by every side. right? So this is the concept which we'll use to build up on it to calculate it for other more complicated shapes, right? We calculate the gravitational field for an element, we integrate to get the total. So this is for a ring. The gravitational force, by the way, will be nothing but GMMA by a square plus r square to the power 3 by 2 if we keep an object of mass small m at this point, right? Let's move on to the next case, which is a hollow sphere. Now the mathematics will get a little bit more complicated, so I'm not going to do it. I'm just going to tell you how to do it, and you can look it up or you can try it on your own, right? It just becomes lengthy, but it's not that complicated actually, right? So a hollow sphere is, we have a sphere of mass m and of radius r, and this is hollow, meaning all the mass is distributed on the surface, right? And we want to find the gravitational field due to this sphere at a distance a away from it, right? Now this a could be outside or it could be inside. This point could be inside the hollow sphere as well. In that case, a would be less than r. Right now a is greater than r, right? We'll take both the cases. So what we need to do is we need to calculate an element's gravitational field, and then we integrate it to get the total gravitational field. We could take many different types of elements, but one of the easiest I see right now is we could take at an angle theta, and we could take a small angle d theta, and we could take these two to make a circular ring, right? Now this is a circular ring. The whole hollow sphere is made up of many circular rings like this. If we take theta to go from 0 degrees to 180 degrees, when theta is 0, we have a small ring at this edge. When theta is 180, we have a small ring at this edge. So theta going from 0 to 180 guarantees that I'm integrating over the whole surface. Right, now I need to calculate the gravitational field at this point due to this ring. Right, the radius of this ring will be r sine theta, and this distance will be a minus r cos theta, right, because this is r cos theta. So now I know the gravitational field due to this ring at this point. I'll just write it down. Be careful about the mass. The dm mass of this element will be the total mass divided by 4 pi r square multiplied by the area of this ring. That will be 2 pi r sine theta, the circumference, multiplied by the thickness, which will be r d theta. Right. So this is the mass of this element. You write the you write the gravitational field due to this ring at this point. Right. We know that it will point towards the left because that's what we calculated earlier. That means all these rings, every one of them, will have a different magnitude of gravitational field, but they'll all act in the same direction. We can add them up and we'll get the total gravitational field. Try it at home and integrate it, and you'll find out that the total gravitational field actually equals gm by a square if a is greater than r and equals 0 if a is less than r. A is greater than r means the gravitational field outside the sphere. It is gm by a square, right? Whereas inside the sphere, if we go inside a hollow sphere, we will not experience a gravitational force anywhere, right? It will be 0. Now, this gm by a square is a very interesting result, right? And in fact, this is the result which enabled Newton to calculate everything he did, right? Because if we have a single particle of mass m and we want to find the gravitational force a distance a away from it, it will be gm by a square towards the left. However, we found out that if we have a hollow sphere of mass m and we want to find the gravitational field at a point a away from its center, now its center because it's an extended object, that is also gm by a square towards the left. So if we want to calculate the gravitational force or gravitational field due to a hollow sphere, we can just assume that it is not a hollow sphere. In fact, it is a particle of the same mass placed at the center of the hollow sphere. You can just take the complete hollow sphere and you can shrink it down to an object of mass m at the center, and it will give you the same result, right? So now let's move on to the final case, which is a solid sphere. Right. So in this case, this whole sphere is completely filled with mass. It's not hollow anymore. It's solid, right? We want to, we want to find the gravitational force and the gravitational field at a distance a away from it, right? This has the mass m and radius r. I can tell you two ways to do it. One would be to do exactly what we did previously. At theta, take d theta and take this. Now this would not be a circular ring, now it would be a circular disk. But that would not work currently because we do not know the gravitational field of a disk. Right, actually we could find the gravitational field of a disk by integration as well. I suggest you try it too. But an easier way would be, in this case I see that it would be easier to instead take elements as disks, to take elements as hollow spheres. So if I take a hollow sphere of radius r and thickness dr, then I know the gravitational field due to this hollow sphere, right? I can write it and I can integrate it. R will go from 0 to capital R, and that will give me the gravitational field due to each hollow sphere, which I can integrate from 0 to R to give me the gravitational field due to this solid sphere. If you try to calculate it, what you'll get is electric field is equal to gm by a square for a greater than r, and it is equal to actually gma by r cube for a less than r. Let's look at the first one first. That is again a remarkable result which we saw for hollow sphere as well. If we have a small particle of mass m and we want to find the gravitational field at distance a away, it is gm by a square towards the left. If we have a solid sphere of mass m and we want to find the gravitational field at distance a away, again it is gm by a square towards the left for a solid sphere as well. That means to calculate the gravitational field due to a solid sphere, you can just concentrate all the mass of the sphere at its center and assume it to be a point particle, right? If we go inside the sphere, it becomes slightly more tricky, and you can do this by integration, or you can do this by another easier way. So if we want to find the gravitational field at this point, let's say we draw a sphere here, every mass inside the sphere, now this is a solid sphere in itself, right? Every point inside this will contribute gm by a square, and you can just add them up to get the total, and every shell outside will contribute 0. Right, because we can divide them into hollow spheres as well, and every hollow sphere has a gravitational field 0 within it, right, inside it. So the gravitational field at a point in this place would just be due to this inside sphere. You do not need to calculate the outside sphere at all, right? Now this is the most remarkable result which Newton was able to use, because he ultimately described the motion of planets, right? And if you have, this is the sun and this is the earth, right, and you have actually two extended spherical objects, right? Let's say this has a distance r1, radius r1, this has a radius r2, mass m1, mass m2, and the distance between their centers is r. Then the force exerted by them on each other will be g m1 m2 by r square, which is the same as the force experienced by a particle of mass m1 and a particle of mass m2 at a distance r away from each other. r1 and r2 do not even matter, right? And this is because if this were not true, then Newton might have created a theory, but he would not have been able to verify the theory by matching it with the motion of the planets. The planets, after all, are not particle objects. He made the assumption that planets are perfect spheres, and with that he was able to calculate a lot of things. Similarly, when we talk about the gravitational field due to the earth, right, at a point on the surface, you could say, well, this point is very close to the surface, so it will attract it by a large amount, this point is very far away, so it will attract it by a small amount. Well, that's true, but when we add the gravitational force due to all of them, the gravitational field comes out to be gm by r square, where me and re are the mass and radius of the earth, and the gravitational force on a particle of mass m comes out to be gmem by r square. Right? So again, we just assume that this whole mass m is concentrated at the center. By the way, this is the gravitational force due to the earth on any object of mass m kept at its surface. We've seen this before as mg. Right? mg is the gravitational force by the earth on a particle near its surface. Right? That's what we used consistently in Newton's laws of motion. So what is g then? G is nothing but another name for this quantity. G me by re square is the gravitational field due to the earth at the center. It is equal to the acceleration due to gravity, and if you calculate this, mass of the earth is I think 6 into 10 to the power 24 kilogram, radius is I think 6400 kilometers. You could look it up, and this quantity comes out to be 9.8 meters per second square. Right? So this tells us that whenever we write in a free body diagram mg, we are actually writing g me m by re square, the force of gravitation between this object and the earth, except we don't want to write this whole thing again and again, so we give it a new name which is equal to small g. Right? The final concept for today is g is equal to 9.8 meters per second square only at the surface. Right? If we move away from the surface, it starts changing. So let's see what happens then. Right? First, let's look at what happens as we go away from the surface. This is the mass m of the earth, this is the radius r of the earth. Let's assume we move a height h above the surface. Right? So now the gravitational force will be gm m, let's take this small mass to be m, by r plus h whole squared instead of by r squared. Right? That needs to be equal to m g dash, where g dash is the new gravitational acceleration due to gravity. Right? So g dash comes out to be gm by r square 1 plus h by r whole square. Right? This I can write as r squared 1 plus h by r to the power minus 2, which I can use binomial approximation, and it gives me g dash is equal to gm by r square 1 minus 2h by r. Right? So which gives me the result g dash is equal to g times 1 minus 2h by r, where r is the radius of the earth. This is as we go above the surface. So we see that as we go higher and higher, the gravitational attraction starts decreasing, which makes sense because we are moving away from the center. Right? What happens if we go inside the surface? Right? Instead of r plus h, this becomes r minus h. Right? I leave it for you to do on your own, but all you have to do is, now the solid sphere which attracts the object has a radius of r minus h, not r. Right? This is again the example of going inside a solid sphere and trying to find the gravitational attraction. This whole spherical shell of thickness h will not contribute at all. Right? So only the inside part will contribute, and that will end up giving me g dash is equal to g times 1 minus h by r. I suggest that you try it at home. It's not that hard. Right? So g dash is g into 1 minus 2h by r as we go above the surface. It is equal to g into 1 minus h by r as we go below the surface. And we see that the gravitational force is maximum at the surface. It decreases as we go above or below the surface. This completes gravitational field. In the next chapter, we'll extend a concept which we've studied before, which is how to define potential energy and potential for a conservative force, in this case the gravitational force. Thank you.